Let me just share my screen. Yeah, we'll begin with the previous year questions for the third week. Or actually, this time what we can do is we can go the other way around. Uh, we can go the other way around. Why I say that is because we'll probably already have gone through these concepts before coming to the questions that are related to these concepts, right? And now in week 3 and 4, in 2 and 3, I have not introduced more of new things in the lecture part of it or in the revision part of it. So it will be quicker also in that regard. Right, so which is why I say that before going into this previous year's questions, we can probably just, sift through the lectures themselves. So it will be kind of a revision, and based on this revision, you can then answer those questions. I think that will be a better way to go. So I can somehow hear an echo. Um, I don't know if that is because of my net or what. I'll just try reconnecting once more, okay? Just give me 1 minute. Okay, I've switched my network again. Hopefully now there won't be any problem.
Hi, Arveen. Arveen.
Yes, yes, yes. Yes, Mavish.
We didn't have any session last Monday because I haven't
Yeah,
received,
we did.
you ha- but I didn't
Oh,
receive any.
any mail regarding the session?
Sorry.
Uh, did you not receive a mail regarding the session? Is that what you just said?
Yeah, last Monday I didn't receive any link to the meeting.
Okay, maybe. Okay, there are two sets of links that they usually send. So this is an automated thing that we have basically planned these sessions at least like 2 months prior to when we are actually conducting them. So we have just planned it and we have given it to the NPTEL team. So they are the ones that are sending the reminders. But since the reminder comes to us also, I don't know if it came on Monday, but one day prior it came last
Yeah,
time also
but I didn't
on
receive any.
Sunday.
I think for the last Monday I didn't receive any link.
Oh, okay. So there is one other thing that the link that I have shared is common only. So every Monday, like I have kept a class from 7 to 9, and the link is also going to be the same. So
Oh, okay.
that is one thing. So in case that happens again, you can, despite that, like it will be okay if you can join. Uh,
Okay.
but okay, maybe somehow it got missed. I received my intimation, although like they sent
Okay.
me an intimation too, so I received one. Yeah.
Thank you.
Okay. Yes. So, yeah, this is what I was saying that until the previous session, we have actually talked about different, like in during this discussion thing, we have talked about things that were outside of what were there in Sir's lectures, also be it the techniques, be it the different regions of the brain, and what these different regions of the brain particularly do. Right? We have like spoken in detail about that also. And which also reminds me that I have not uploaded that session yet. So that also I will do. I'll probably upload both of them together by tomorrow or by Wednesday maximum. So that was that. But me also being a biology background student, I have not had much inputs for this particular, unit two lectures. So that I have kept it as it is. We are just going to sift through. We are just going to go through this concepts once again. It is going to be kind of like a revision. And along with that, we are I'll emphasize on the pointers that you should remember, right? From where the questions can be picked up and where the concepts can you need to grasp those concepts. Those things we lay more emphasis on, right? So I have not kept any additions to this unit 2 lectures at least, right? So we are just going to go through it as a revision series. So yeah. Yes. So, in this unit two, you basically began to draw comparisons between the electrical circuit as well as the neuronal circuit, right? So, we had already discussed regarding this that why and how the neuron is similar to an electric circuit, right? Because over here also, like over there is a flow of charged particles. Over here also, there is a flow of charged particles. In case of the, nervous system, these charged particles are ions, right? Usually, in case of electric circuit, it is electrons, but over here, it is ions, right? So it could be positively charged ions, negatively charged ions, divalent ions, monovalent ions, different kinds of ions are there, and their transfer into and out of the plasma membrane will basically cause different, charges, and this flow will generate current, right? So the current, as we know it through our basic physics that we have all studied, that it is denoted by I, right? And the unit of this current is ampere, right? But when we are talking about a biological system, whether we deal with ampere worth of current, right? That much current do we deal with? No. So in case of neuroscience, we usually deal with very minor, scales of current. Now, what are these scales? They are generally nanoampere or picoampere of currents, right? More often nanoamperes than pico, right? So that is 10 raised to power minus 9 ampere or 10 raised to power minus 12 amperes, right? Also, what is going to be the direction of the current? It will basically always be same as the direction of the flow of positive charge, right? So, if the flow of electricity is opposite to the flow of electrons, right? Because electrons are negatively charged, and meaning that their direction and positive charge direction is going to be opposite. And wherever positive charge direction is there, the electric current is also going to flow in the same direction, right? Similar is the case over here, but over here, directionality is less of a concern for us, right? Opposite of the direction of the flow of negative charge. That also we have established, right? So the circuit we'll discuss once we build on more into the circuit, right? So, yes. So then we come to voltage, right? So voltage is denoted by V. Voltage basically stands for the electrical potential difference, right? So that is the difference between two nodes or two electrodes is going to be the potential difference, right? So that much can actually, like the circuit has that much potential and it can pass that much current through it, right? So it is a driving force for current. It is always measured between 2 points, right? So it is always a relative quantity. I cannot see that potential difference for this one, right? Then what is it a difference between, right? It has to be a difference between something. So that is why it is always a relative quantity. The unit generally is volts. In neuroscience, the scale of this unit that we generally deal with is millivolt or 10 raised to power minus 3 volt, right? So, the potential difference that we talk about over here is between the outer side of the plasma membrane and inner side of the plasma membrane, right? So that is the difference or potential difference that we talk about. Then comes resistance, right? So this is the final one in that formula, V is equals to IR, right? So resistance is denoted by R, its unit is ohm. What does it mean? It means to something that impedes the flow of current through a medium, right? So resistance, normal English word, it is a normal English word, and in English also it means to cause something to stop or to resist something is to basically come in its way of happening, right? So yeah, so over here what is happening, resistance is being caused basically to slow or impede the flow of current that is happening, right? So the unit, as I said, is ohm, but in case of neuroscience, the resistance is much higher, right? So over here we deal with resistance in the power of 10 raised to power 6, that is mega ohm or giga ohm, which is 10 raised to power 9, right? So various channels in the membrane can conduct current and have different resistance values, right? So I have a question, like if for your better understanding, why do you think that although the voltage is lesser because it is a smaller system, the electric current is lesser because it is a smaller system, why is the resistance so much, right? So both of them were in the power of minus 9, minus 12, minus 3, and over here it is a positive part, 10 raised to power 6, 10 raised to power 9, right? Why do you think that will be?
To
I still
avoid any
can't.
misconduction.
To avoid any misconduction. Okay. No, just think about it in a physical, with the, with physics in mind, not particularly this thing.
The
So,
current is inversely proportional to
yeah,
resistance. More is the resistance,
yes,
the lesser the current will flow.
yes. And if you logically try to think about it, even if we did not know this formula V is equals to IR, right, where we know that voltage is directly might be proportional, but it is in current is inversely proportional to resistance, right? We can also think of it in a more logical sense, wherein if you take a thicker pipe, the water flow is going to be smoother if you are sending the same amount of water through it, while if you take a thinner pipe, the water flow is going to be impeded. If you are trying to send the same amount of water in the same flow, it is not going to, go, either the pipe might burst if it is just a plastic thing. If it is a metal pipe, it might go, but it might go slower, right? So over here in the biological system, what is happening is the neurons are like in microns, right? So they are very, very tiny. And over here, we are not even talking about microns because that is the entire neuron, right? We are talking about the cell membrane of a neuron or plasma membrane of a neuron, which is going to be in further, lesser microns. So that is why this kind of a thing happens, right? Because if the dimension is reducing, resistance automatically is increasing, right? Because it is going to be very, very difficult for something to pass through that narrower thing, right? So that is why resistance is much higher in case of our biological system. Yeah. So this was an analogy, right? So the water flow analogy, that if the hydraulic pressure difference was seen, that is basically considered as the voltage difference over here. The charge would be the quantity of water. If I had a full bucket of water over here, that would be I can say that it is a full charge, right? And the flow rate of water is going to be the current, right? We can draw this analogy that the flow rate from which it flows from this tank to this tank, it will be the current of flow of that particular charge, that is water, right? So if this is the conducting wire, obviously the resistance is going to be low. But if the conducting wire has a very, very narrow, region, the water flow is going to get impeded over there, right? It is going to get terribly slow. So that is why it can act as a resistor, right? So it will have a very high resistance. Okay. So we know this formula, V is equals to IR, that is potential difference is equals to the current into resistance, right? So if we look at the SI units, generally it will be 1 volt is equals to 1 ampere into 1 ohm. But in neuroscience, the more common units that we will deal with is 1 millivolt, which makes total sense, right? It will eventually be this same thing, right? It will eventually be this only. So 1 millivolt is basically 10 raised to power minus 3, right? Is equals to 10 raised to power minus 9 nanoampere, it is written, into 10 raised to power 6 mega ohm, right? So this also, when it goes over here, it will be added. It will be 10 raised to power minus 6 is equals to 10 raised to power plus 6. It will basically, the sign is all the difference that there is going to be, right? So this is what is a kind of units that we deal with in neuroscience, right? Then there is another terminology that was introduced to you, which was conductance, right? Now, what was resistance? It was basically just impeding the flow of something. What is conductance? It is another property of the same, charge, that when we were impeding its flow, it was known as resistance. Now, if we look at how fast or how smoothly it can flow, that is going to be the conductance. So, right? So, it is the inverse of resistance. It is the ease with which a current can flow, and it is denoted by G. Right? So G is equals to 1 by R. That is, it is the inverse of resistance. Its unit in generally is Siemens, right? But it is also denoted as ohm inverse, right? So 1 by ohm, that will be ohm inverse, right? So we can write it as I is equals to V by R, or I is equals to VG, right? So in that case, we can write V is equals to IR, or V is equals to I by G, right? So that is also there. So the more the conductance, the more the current for a given voltage, right? Then comes capacitance, right? So now this again is a new terminology that was introduced in context of biology, I'm saying. What was capacitance? It is a capacity to store charge, right? So that is what capacitance means, right? It is also pretty derivative from its name. So two conductive layers which are separated by a dielectric or an insulator basically shows capacitance, right? It accumulates charge when voltage is applied. It is denoted by C, right? And C is equals to Q by V, where Q is the charge and V is the voltage. The unit for capacitance is farad, and the relevant unit in neuroscience is going to be picofarad, right? That is 10 raised to power minus 12 farad, right? So this is the symbol of capacitor. In case of neuroscience, where what is basically a capacitor? A capacitor could again be this, plasma membrane, because although it lets for some charges, it has channels that it can let these charges pass through, but mostly you also might have studied it when you were studying this membrane biology, if that you have studied, right, in your cell biology. It is a subtopic of cell biology itself, that the outer membrane is more positively charged. The outer side of this plasma membrane is more positively charged, and the inner side of this plasma membrane is more negatively charged, right? It has to do with the proteins that are present within the membrane, plus the ions that are surrounding the membrane also, right? So inside we know there is more of fluoride, there is less of positively charged ions, right? Like in totality, obviously there is more potassium, but in totality they are lower than what is there outside, right? Outside there are so many more positively charged ions. Magnesium is there, calcium is there, sodium is there, right? And comparatively lesser negatively charged ions, right? So one side will become a positive, accumulate positive charge, the other side will accumulate negative charge, and thus it is also acting as a capacitor, right? So when we were drawing an analogy with water flow, in that a rubber membrane, if we draw in the middle of the wire through which we were flowing water, that will act as a capacitor, right? Because now what will happen, the charge is not physically going from this end to that end, but the current is still going to flow, right? So over here, water pressure difference will be the voltage, water flow is the current, water is the charge, and narrow pipe is the resistor, right? Yeah. So the current flow through a capacitor, even though no electrons move across it, right? So that is what I was saying. Charge is not flowing across it, right? There is no electrons that are moving across this end to that end. Still, the current can flow, right? Uh, because there is a directionality that is still present over here, right? So current changes charge stored on a capacitor. So when a capacitor is charged, it creates an opposing voltage. After a while, the opposing voltage will be equal to applied voltage and the current flow will stop. The capacitance value tells how much charge can be stored, right? So that is what it informs. Now, this was an example of the capacitance in neuronal membrane, and we will discuss maybe in the numerical or over here itself, that if a charge is applied, where do you think it will flow first? Will it flow towards the resistor or the capacitor? Why will that happen, etc. Right? So when we look at these components we have now learned, we can see these things. That resistance is inversely proportional to surface area, right? The more the surface area, the lesser the resistance, right? If the diameter of the tube is wider, the resistance will be lesser, conductance will be higher, right? Capacitance is proportional to surface area. The more the surface area, the more charge it can accumulate, right, on that surface area. Sometimes we talk about capacitance and resistance per unit area, right? Maybe we do that right now also. Then we can talk about membrane potential in neurons, right? So this is one of the model organisms for the study of membrane potential. It is basically the squid. And this squid has a very specific neuron, which is known as the giant squid neuron, right? Why it so widely studied? Because this neuron has a very large axon that is 1 mm in diameter, right? 1 mm in diameter, that is like too big. Like the axons in our brain, you will not even be able to differentiate between them with naked eye, right? But 1 mm you can see, right? So that is why it is big. And because it is big, it was easier to study, right? So these are the ion concentrations in the squid giant taxon that are given. Uh, so three main ones are listed over here: the potassium, sodium, and chloride. Right. So you can see that the relative concentrations are present inside and outside the extracellular matrix. or the plasma membrane, right? So in case of potassium, we see that in the cytoplasm has much higher concentration as compared to its concentration in the extracellular matrix. Sodium and chloride, both of them have much higher concentration in the extracellular fluid as compared to inside the cytoplasm, right? And these along with other ions, like their relative concentrations inside and outside the cytoplasm, they basically determine something that is known as resting membrane potential or the stable membrane potential of any organism. In case of the squid giant taxon, this is minus 65 millivolt, right? And how has this been achieved through, multiple equations, the GHK Nernst equation, which also we have discussed also during last week's question answer sessions, and briefly we'll go over that right now as well. So at rest, when we look at it, you can see that this is the outside or extracellular space and this is the cytoplasmic side, right? So in the cytoplasmic side, what can you see? What are the concentrated ions? Okay. So when you talk about negatively charged ions, right? Negatively charged ions, you will see that there are more number inside the cytoplasm, right? These anions that are labeled as A, specific anions such as chloride that are also labeled as Cl, this yellow color, right? So they are more, commonly found inside the cytoplasm as compared to in the extracellular matrix, in the extracellular solution, right? Uh, if you look at the positive ions or the cations, right? You can see inside there is an abundance of these green colored circles that is, representing potassium. But apart from this, more cations are actually present towards the extracellular solution, right? Be it sodium represented by this blue colored circles or this purple colored circles that are representing calcium, which are actually divalent. So double the positive charge they have, right? So from this also you can visually see that the the ions that are concentrated outside are usually sodium, calcium and chloride, and overall they render a more positive potential. And inside the more concentrated ions are the potassium and other anions, including chloride, but not limited to it. And these altogether render a more negative potential. Yeah. Then how do we actually measure this membrane potential, right? So it is measured by something which we have previously already studied when we were looking at single unit and patch clamp, right? So these two, when we were looking at, we have already studied this technique of how membrane potential is studied, right? So what happens over here, an electrode is present. This electrode is a recording electrode, right? It is inserted into a single neuron through some point in its plasma membrane, and the voltage is basically measured via this amplifier that is present, right? Amplifier and oscilloscope that is present. It will basically tell you the readout of what amount of volt is there, right? So, in case of this is kind of the display that this kind of an oscilloscope setup will have, right? In case of giant squid axon, this display is actually true that it is near minus 65, right? The resting potential of that neuronal membrane will be around minus 65 millivolt, right? Yeah. So, this same kind of setup, again, this also we have studied when we were looking at single unit and patch clamp, that this kind of a setup can also be used to generate or to stimulate the neurons, right? So over here, what is going to be different? There is still going to be a recording electrode, an amplifier and an oscilloscope to actually record this stimulation, this response to stimulation, and there will be a stimulating electrode also, wherein we will generate some current, and based on what kind of current we are giving, it will either current will flow into the electrode or from the electrode, right? Depending on what kind of current it is, right? So if, for instance, negative current is being passed, then it will lead to hyperpolarization, and current flow direction will be from negative to positive, that is from inside to outside, right? So what does hyperpolarization mean? This also we have studied last time, right? So in this case, in this setup, what is polarization, or what is polar in general? So polar basically stands for something that is not.
Hello.
Okay, I'll continue. So yeah, just a moment. Yes. So polarization over here is a negative value, right? One second. Admit the participants. That is why I think there is a problem with the internet. But anyway, I'll just continue. Okay, I'll share again once more. Yes. So what we were saying over here was that there is a polarized state that this neuronal membrane already is in. This polarized state over here is at minus 65, right? Now, what will be depolarizing? It will be taking it to a neutral state, right? So, depolarizing a polarized something that is already polarized over here will be it going closer to the value of zero, right? And hyperpolarizing will be to take it further away from the value of zero, right? So if a negative current is actually applied, it will be hyperpolarizing, right? Because it will cause its membrane potential to become further more negative, which will increase its polarized function. So it will be hyperpolarized now, right? So if it is going closer to zero, it will be depolarized. Yeah. if, for instance, a positive charge was passed, what will happen, right? The membrane potential will be depolarized, right? It will go closer to zero. And if a certain threshold value is reached, it will even turn into an action potential, right? Now, we'll later discuss what this action potential is, right? So, what determines the speed of change of the membrane potential, right? So, if we are giving this much positive current, only this much of it is rising or it is becoming depolarized, right? However, sometimes even action potentials are causing that much of depolarization, right? This is charging or discharging of membrane, which again we have actually gone through last time. I want to come to the answer of that one. Okay, so I think, okay, we'll discuss charging and discharging of membrane then. So, if a constant current is applied, if this current is flowing from inside to outside of this plasma membrane, initially more of the current will flow through the capacitor, right? And less of it will flow through the resistor. Why? Because the value of voltage will not change in this case, right? But as the current starts flowing through the capacitor, what will happen in the capacitor? A charge will start developing, right? So there will be a charge that it will start, depositing on itself. So as it develops a voltage, the current will also now start flowing through the resistor, right? Now the voltage across the resistor and capacitor must be same at all times. That is why this is going to happen. Then this current flow through capacitor will decrease, right? Initially it was flowing through capacitor. Once its voltage increase, now it will flow through resistor more often. And during this time, this, accumulated charge on the capacitor has also dissipated a little, right? So it will decrease and the current through resistor will increase, right? Eventually, all the current that is applied will flow through resistor and capacitor will reach a stable voltage. So that is how the charging or discharging of the membrane would occur. If the current source is removed, right, the discharge current will flow through the resistor and the voltage across capacitor will also reduce gradually. Eventually, it will return to neutral position and no current would flow at all, right? So when we are charging this membrane, right, because it is getting charged in very little time, we are talking about it, right? So the charge across capacitor is Q is equals to CV, charge is equals to capacitor and voltage across it. So if we say that it changes very little in a very little time, right? So a small time will be denoted by dt and little change will be denoted by dq, little change in the charge, right? So it will also cause a small change in the voltage, right? So dq is equals to c dv, right? If we say that this much is changing in this much time, that is small time, so dq by dt is equals to c dv by dt, and the rate of change of the proportion is proportional to rate of change of voltage, right? The derivation for this, if you want to study it, is beautifully given in Candle, right? So you can again go and look at it. This is further, the derivation of that formula, wherein, it is further including the time constant as well, right? That is the tau. So this is the tau that was listed over here in this formula. That is V is equals to V naught E raised to power minus T upon RC. That is resistance into capacitance, which is also termed as tau. Right. So what is this tau? It is resistance into capacitance. It determines how fast or how slow the capacitor will charge, and it is known as the time constant of the membrane, right? Because it is determining the speed of charging, right? So it does not depend on the area of membrane. Of course, because if a large area is present, the capacitance will be larger in proportion to the area, and resistance will be smaller in proportion to area. So individually, these components are affected by the surface area, right? Lesser surface area means more resistance, lesser surface area means lesser capacitance, right? But because these two are, inversely proportional to surface area when we are talking with respect to one another, right? Resistance is inversely proportional, capacitance is directly proportional. So it will be surface area upon surface area, right? So overall, tau does not depend on the surface area or area of the membrane, right? So time constant is rather dependent on properties of membrane such as density of ion channels, thickness of the membrane, etc. Right? So this tau is a dimensionless quantity. It has units of time. That is second inverse actually. Right? So tau is equals to RC in a neuronal membrane. Since R is in order of mega ohms and C is in order of nanofarads, the tau is in order of milliseconds, right? Okay, this is that when tau is basically t is basically zero, uh, that is when V becomes equals to V naught, and this is when voltage has become approximately 0.37 of its original value, or tau is the time in which voltage has reduced by, or potential difference has reduced by 63%, right? There was another value that we had discussed last time, which was this is the discharging and the charging of the membrane time constant, right? Then we had also discussed about the length constant, right? So length constant of a branch of neuron basically is dependent upon how big the surface area is, right? Because if it is this much, it only has to dissipate across this much, right? If it is this big, it has to dissipate across this entire length, right? So that will differ, right? If not the same amount of current will dissipate across its entire length, right? Uh, so again, if there was a current generator and current was introduced, it will keep getting diminished by the point it reaches by the time it reaches the farthest point of this tube that is represented over here, and it will be highest in the closest vicinity and lowest in the farthest point, right? So this graph represents again is charging and discharging, where x is the distance and lambda is the length constant, right? So this length constant is actually, in the same equation when we see. So V is equals to V naught e raised to power minus x by lambda, which is an exponential decay situation. The maximum value is reached when x is equals to 0, right? So over here in this previous diagram, if you see x is equals to 0 over here, at this point, the length constant will be maximum. At this point, it will be minimum, right? So when x is equals to 0 point of injection, that is denoted by delta V naught. Rate of decay is determined by the parameter lambda, right? If lambda is equals to 1, value becomes delta V is equals to delta V naught e raised to power minus 1, or it becomes 37% of its maximum value, right? It tells in how much length does V reduce by 63%, right? So this is the value of lambda. Lambda is equals to under root Rm by Ra. Now, what is Rm? It is the membrane resistance, and Ra is the axial resistance, right? So, if the membrane resistance is more, right, it is about, if you look at it like an insulated wire, right? Insulated wire has more resistance on the membrane, right? Across its surface, it has more resistance, right? So that is why it is less leaky, right? If it is not insulated, it will the current whatever is passing, like this, it can also pass like this, right? But if it if it has insulation on it, it has more Rm, then it will have lesser leakage of current in this direction, right? Opposed to axial resistance, right? The more the axial resistance, the lesser current will flow and the more hindrance along the path it will face, right? So I hope this point is also clear. So what is the relationship between length constant and axon diameter? Rm depends inversely on surface area, right? More surface area, more lesser Rm. Thus, Rm varies as 1 by 2 pi r. Ra depends inversely on cross-sectional area, this one, right? So it varies as 1 by pi r square. Rm by Ra is proportional to radius. In other words, length constant increases with radius. And what is the significance of this? That thicker axons will allow conduction of electrical signals with lesser attenuation, right? So that is actually true. That is what is happening in case of the giant squid axon also. So a time constant tells you how slowly the signal changes in a neuron, and length constant tells how far the signal spreads in a neuronal branch, right? So this was for the unit 2. Whatever I had kept in this particular presentation, there is still part of unit 2 that is remaining that we had picked up in this one, right? Wherein the driving forces for these currents were being talked about, right? So this driving force could either be a concentration gradient or an electrical gradient. Last week we had actually done a couple of questions in regard to this, right? So if whether the concentration what was the question? It was something like potassium is more on the inside and less on the outside. Based on the concentration gradient, what do you think? What will be the flow of solely based on concentration gradient? What will be the direction of movement of the potassium ions? Right. So that was the question. Right. We had answered that also. So what do you think would have been the answer for that? They had mentioned that solely you have to think about the concentration gradient only. And based on that, what do you think in this case also? You see, chamber A has this kind of a gradient and chamber B has this kind of a gradient, right? So solely based on concentration gradient, what do you think where or what direction will be the flow of potassium ions?
From chamber B to chamber A, more
Yeah,
clearly.
right. Right. So when we are talking about concentration gradient, it is always dependent on one individual ion, right? And that one individual ion is more in chamber B, the potassium ion, and it is lesser in chamber A. So it will obviously be from chamber B to chamber A, right? But now, if we look at the electrical gradient, right, over here it might not be representative, but they have mentioned over here that chamber A has a positive electrical gradient and chamber B has a negative electrical gradient, right? So if we look at only the electrical gradient, what do you think will be the response for this? So chamber A is positively charged and chamber B is negatively charged. Now, what do you think? What will be the flow of potassium ions? Which direction? Okay, so in this case, it will be from chamber A to chamber B, right? Because a more positively charged ion is going to a more negatively charged chamber, right? So it is a positive ion in a positive chamber versus, there is a negative chamber nearby. So if it talks, has to think about the only the electrical gradient, then it will move from chamber A to chamber B, right? And the resultant gradient, actually, whenever we see it, is a balanced out version of both the concentration gradient and electrical gradient. We'll study that in this discussion, right? So, yeah, when we talk about potassium ions again, if we open the potassium channels and allow ions to flow out, right, from inside the cytosolic side to the extracellular side. This is the energy that is released per mole, right? if this ratio is more than 1, the ratio of ions is inside is higher and ratio is positive, right? And positive energy is being released when potassium moves out, right? But when we talk about electrical gradient, again, this is the example that I was given. The energy released per mole for inward movement is going to be higher. It is minus Z EF, where Z is charge of ion, F is the Faraday constant, and E is the membrane potential. And energy is released per mole for outward movement, that is ZEF, right? Because potassium ions are positively charged, they will be attracted towards negative potential, that is inside the cell. Although concentration gradient was driving potassium ions from inside to outside, electrical gradient is actually willing to bring them from outside to inside, right? So this is what happens. So at equilibrium, there has to be an equilibrium for each ion that has to be reached, right? So for potassium, when we are talking about it, at equilibrium, the net charge or net change will be zero, right? No flow of ions from inside to outside or outside to inside. Now, how will that be achieved? This is the equation for that. It is known as Nernst equation, named after Walter Nernst, who formulated it in 1888. Right over here, E is equals to RT, right, upon ZF log of concentration outside by concentration inside. Right. So R is the gas constant, T is the absolute temperature in Kelvin, F is Faraday's constant, Z is the valence of the ion. If it is monovalent, then 1. If it is divalent, then 2. Right. And then XO and XI is the concentration outside and inside the cell. Right. So this is another shortcut for the Nernst equation, wherein because these are constants themselves, and if T we are taking at room temperature itself, it is always going to be 298 in that regard. So if we are calculating for this RT and F, this is the equation that we get, right? We can directly put it anywhere if provided the temperature that they are, either they have not stated a temperature wherein we can always take it as room temperature, or they are stating it as room temperature, right? So we know this is a concentration inside the cytoplasm and outside the cytoplasm in case of for potassium ions in case of giant squid axon, right? If we apply the Nernst equation over here, what is the outcome that we will get? Right? So we will get the outcome as minus 75 millivolts. That is going to be the equilibrium potential for potassium ions, right? So electrical gradient and chemical gradient for potassium ions will be balanced out at what voltage? Minus 75 millivolt, right? Again, it is a high, more polarized, and its resting potential also. So at minus 75 millivolt, if membrane potential is equals to this value, then there is no net movement of potassium ions because electrical gradient as well as concentration gradient has been balanced out, right? Then what will happen if membrane potential goes below minus 75, right? What if it is, sorry. What if it is minus 60 or minus 50, right? Sorry, below minus 75 will probably be like minus 80, right? So then electrical gradient will become stronger and attract key positive ions, which will bring the potential back towards minus 75 millivolt. Right. And what will happen if membrane potential goes above minus 75 millivolt? Then what will happen? Then it will become weaker, the chemical gradient will become stronger, and this chemical gradient will push some of the potassium ions outside to balance out and to bring the membrane potential closer to minus 75 millivolt, right? So over here, the important point to notice that the concentration gradient changes more slowly than the electrical gradient, right? Now, why is that? Because obviously electricity is going to travel faster, right? That is because of faster travel of ions, right? So this you can remember through, the speed of electricity that is always going to be faster. Then this is the representation of a single potassium channel without concentration gradient, right? In the absence of this concentration gradient, this is the potential value, right? And this gamma K is equals to 1 by RK, right? So gamma is the conductance of a single channel and R is the resistance basically of that single channel, right? And through Ohm's law, I is equals to gamma K into V, right? When a concentration gradient is present, then E equilibrium potential is not equal to zero. There is no ionic current when V is equals to EK. But if V is equals not equal to EK, then current will flow through the channel and the slope will determine what is the value of gamma K or the conductance, right? If V is above or below the equilibrium potential, it will result in potassium current, and this will be the formula for that current, right? Now, similarly, there are other ions also that follow the same kind of theory, right? So, similar is the case for potassium and similar is sodium and similar is the case for chlorine, right? Now, equilibrium potential for chlorine is also negative. It is minus 60, but for sodium, actually, it is a positive value. It is plus 55, right? And you know that the resting membrane potential is what? It is minus 65. So, it is closer to potassium and chlorine's equilibrium potential, but it is very, very far away from the equilibrium potential of sodium, right? So you know that there will always be a much more flow of sodium ions into and outside because of both the electrical and the chemical gradient than potassium and chlorine, right? Yeah, so this is, an equivalent circuit showing various kinds of ions and, over here, because this has a positive equilibrium potential, the battery over here has been inverted, but it could also have remained the same and the signs could have been inverted. That could also have been done, as Sir had already told, right? So, usually at rest, there are more potassium ions open than sodium channels, right? That is the situation at rest. So, if we consider the case that when only potassium channels are initially open, right, then what will happen? A few sodium channels are then opened, right? Initially, potassium channels are open. Potassium will obviously move across outside towards its lesser concentration gradient. Then, धीरे what will happen is a few sodium channels will also be opened, right? Now, initially, when only potassium channels are open, it is the driving force, right? So, chemical gradient, which is in blue arrow, it is driving potassium outside and the electrical force is driving it inside, right? So, it is the only driving force. When a few sodium channels also start opening. Now in case of sodium, both the driving forces for chemical and electrical gradient are towards the inside, right? So now this will become the net driving force and both of it will go inside. The net current will be inside, right? Then eventually a steady state will be reached wherein the net current will be balanced out, but there will be more driving force or more ions that are coming inside than the ones that are going outside, right? Yeah. So at steady state, the potassium ions are continuously trying to reach minus 75 millivolt potential. So they are moving out. The sodium ions are continuously trying to reach plus 55 millivolts. So sodium ions, they are pushing inside, right? And if the sodium and potassium currents are balanced out, the membrane potential stay as VR or the resting membrane potential. So this is the circuit that is determining the resting membrane potential, and this is the formula for the same, right? It comes to around minus 69 millivolt. And this value is simply not an average of the three values, but it is in a weighted average, right? And it is weighted by the conductance. What it means is that it is not like minus 60 plus minus 75 plus 55 upon 3, right? It's not just a normal average or mean value, something like that. What it actually is, a weighted average, that if there is more flow of potassium ion, then potassium will get more weightage in this calculation, right? If there is lesser flow of chloride ions, it will get lesser weightage in this calculation, and so on, right? Depending upon the abundance of ions also, only not just their charges. We know that the conductance of potassium is highest in the resting state. Therefore, it is not surprising that the value comes closer to the equilibrium potential of the membrane. Right, so that is the reason, because it is a weighted average, and potassium is the highest, has the highest conductance in the resting state, because there are more potassium ion channels that are opened at that time. That is why equilibrium potential of membrane is similar to the equilibrium potential of potassium, right? And this is a simplified representation of a resting membrane, wherein the passive channels altogether that are like randomly opened, like the sodium channels that are opening later, potassium channels that are open at most times, right? They are called the leakage channels, right? Because they are letting the current and concentration leak out. So, if we assume that potassium, sodium, and chloride currents are balanced out, membrane potentials stay at the resting membrane potential VR, but it cannot go on indefinitely, right? Why? Because these concentration gradients are maintained in parallel by the active transporters, which again we have studied in the first session, I think, which were the sodium potassium pumps, right? This is the representation for the semi-K pump, which is going to take it across, against the concentration gradient. It is going to throw sodium outside and potassium inside, right? And it is much more faster also than the flow through channels. Now, this is the final equation, which is known as the GHK equation, which is Goldman-Hodgkin and Katz voltage equation. When we are, listing different major ions and the membrane potential depending on all these major ions, right? This is generally what we get, that K to Na to Cl ratio is generally 1 to 0.4 to 0.04 to 0.45, right? Yeah. So this is just the equation. I'm not getting into it again, right? Then comes the action potential. Let me just see the time, whether we have time to go through the, yeah, we will have time. Maybe till 8:15 we can discuss this. Then whatever is left, we can pick up next time. Because anyway, we are going faster only in the revision, and we can go and do the PYQs. We can at least complete that. Okay. So then we come to action potential. As I told you that whenever a positive current is applied, only a little polarization happens over here, right? Depolarization, right? And these little changes are known as electrotonic potential, right? But sometimes the current is enough so that this depolarization actually reaches a threshold above which, if it goes, it causes a sharp spike, and this sharp spike is known as the action potential, right? So when we apply a small pulses of current, we see small changes in the membrane potential, but if large positive current is applied, we see different type of response, which is known as action potential, which has large and rapid increase of membrane potential, and there is a rapid fall, right? So over here, gradual increase, gradual decrease, Gradual increase, gradual decrease. But over here, there is rapid increase, rapid decrease, right? So what is determining this action potential, right? These ion channels again are going to be the cause of this action potential. These ion channels are built up of proteins that line a water-filled pore that allows ions to flow through. They are basically going to conduct ions at higher speed, and they recognize and select specific ions, right? For example, the potassium ion is only permeable to potassium and not sodium, or a little bit of sodium it can let it pass through, but it is 100 times more permeable to potassium than to sodium. While in case of sodium, it is 15 times more permeable to sodium than potassium, right? Although these two are very, very similar, monovalent ions, cations also. Some channels open and close in response to specific electrical, chemical, or mechanical signals. If we just look at the size of these, ions, you can see that potassium has a size of around 0.133 nanometer, while sodium has a size of about 0.095 nanometer, right? So they are closer over here to represent, of course, because it has a difference of about 0.40 nanometer, which is also very small. We have represented them like this, right? So how does channel allow potassium ion to pass through while not sodium ion? Now, how does that happen, right? If it has to do something with the size, right? If it is built because of a bigger size, only it will let it pass through. Then sodium can also fit into that range, right? If it was a sodium ion channel, which based on size it was selecting, it could maybe let the sodium ion pass and not the potassium ion, because it will get stuck. It will not be able to pass because of its bigger size. Then it would have made sense. But what we said instead was potassium channel is more, uh, permeable, like it is 100 times more permeable to potassium than sodium. So how does it differentiate, right? Because sorry, because there is a aqueous medium or a crystal radius that is also going to be present, right? So this aqueous medium will surround the potassium ions, due to which its effective size will become bigger, right? So it contains many water molecules. The red oxygen atom and the white are the hydrogen atoms. The oxygen atom is more electronegative than the hydrogen atom, and it tends to attract the negative charge towards it, creating a partial negative charge on the oxygen and partial positive charge on the hydrogen atom. So Na or K tend to attract these partially negative oxygen atoms because of their positive charge, right? So eventually, as a result of this, sodium ion is never present in isolation, rather always surrounded by a bunch of water molecules. It increases its effective diameter of the whole molecule, and these bunch of water molecules is known as the hydration shell. The ion with the hydration shell has a much larger radius than the ion alone, right? So this is what the smaller sodium ion, because of more localized charge, attracts more water, right? Localized charge is there, more water is coming, it is more electronegative charge is being attracted, so the hydration shell is larger, right? The larger potassium ion is attracting lesser electronegative water ions, so the hydration shell is smaller. So it is based on size, but size after the attachment of this hydration shell. So as a result, sodium behaves as if it is larger than potassium, right? So that is why that statement holds true, that from the potassium ion channel, it is 100 times more permeable to potassium than to sodium. But in case of sodium ion channel, it is only 15 times more permeable to sodium than potassium. That is because this is a smaller, ion than this. So through leakage channels, it can still pass, right? So this is what happens. So how do sodium channels become specific for sodium? These ion channels are not rigid tubes. They have proteins that interact with surrounding molecules. The ion channel for sodium has a selectivity filter. Right now, what is the selectivity filter? Its proteins are made up of amino acids that have various kinds of side chains. When ions are passing, they interact with the side chains of amino acids with this channel. And typically, ion channels have a narrow region in the middle, which is known as selectivity filter, right? Over here, hydration molecules are actually coming off, and over here, the selectivity filter has a tiny gap only, right? They have a narrow region. That is why it is a selectivity filter. In these narrow regions, hydration shells cannot pass through intact, so water molecules are stripped off, right? So only the sodium will pass through, and then again it will be reattached with this hydration shells after it has passed. So only sodium, not potassium ions can remain. And removal is an energetically unfavorable reaction, but it can take place because sodium or potassium can be stabilized by interaction with negatively charged amino acids. After this, ions can pass through and it can regain its hydration shell. Interaction will depend on exact positioning of these various amino acids, right? In sodium atom, the positioning is such that the sodium can be fully stabilized, so it is optimized for size of sodium, right? This selectivity filter is optimized for size of sodium. Then there are gated channels, right? There are some ion channels that may have two or more conformational states that are stable, right? One could be an open state, the other is a closed state. That is why it is known as a gated channel. The transition of channel between these states is called gating, and such channels can be called as gated ion channels, right? So what happens in these gated ion channels? Sometimes there is a conformational change in one region, right? So over here it is in an open state. Over here, because of conformational change, it has come to a closed state, right? Or there could be general structural change. It is open at one time and it becomes very, very tiny and, contained in this other region. Or there could be an additional thing that is attached to this channel that may or may not block the channel, right? So there are multiple types of stimuli also that control the opening and closing of ion channels. They could be ligand gated, wherein they are opened or due to the binding of a ligand. They could be voltage gated, wherein after a certain voltage is achieved, the channels open. Or they could be stress or pressure gated, wherein maybe the touch or tactility that can open or close a ion channel, right? Okay, so this is where we will pick up next session. Okay. For now, I'll just switch my presentation, and what we'll do is the PYQs for this week, right? Yeah. So I'm glad the first question we have just gone through, right? So I hope you can answer. Hydration shell of potassium ion is smaller than the hydration shell of sodium ion. Is it true or is it false? Yeah. Yes, Mavish.
The statement is true.
Yeah, so it is true. This is literally the last thing that we have studied, right? So that is why we are not repeating it right now. Okay, just the statement we'll read that potassium ion indeed has a has the same amount of charge, but over a larger volume. So its charge density is also lower, right? Then in current clamp, we measure the current by controlling the voltage. Is this statement true or false? Do we control the voltage?
False.
Yeah. So it is false, right? We are measuring the voltage and we are controlling the current, right? The input or the output, positive or negative current is what is being supplied. And what we are measuring actually is the voltage, right? Then again, a true false statement. In the voltage clamp, the compensatory current is positive when the net ionic current is flowing out of the neuron. Is it true or is it false? So,
I guess true.
okay. So what I mean over here is that when we are stimulating, right, is it positive current when the direction of flow of current is towards the outside of the neuron? Then is it positive or is it negative? So here they have mentioned it as positive, right? So yes, if the net ionic current is flowing out, right, then we have injected a positive current into the cell to maintain the desired voltage, right? This is an example of the same. So, yeah, the ionic current is balanced out by compensatory current, right? So, this is the compensatory current. This is the ionic current, right? No, this is what is being measured. This is the ionic current, right? So, V does not change. The measurement of compensatory current tells us the value of ionic current, right? So, okay. Entire thing, I think I have not spoken about as of now. We'll discuss it in the next session. Okay, there is just one component we have left, that is the compensatory current, right? So I'll come to it in the next session. So, which of the following is true about the structure of an electrical synapse? A pore is made from a single protein chain that passes through both neurons. A pore is made of 6 protein chains, all of which pass through both neurons. A pore is made of 12 protein chains, 6 of which pass through each neuron, or a pore is made of 24 protein chains, 12 of which pass through each neuron. Now, again, this part we have not come to as yet, um, but if you have gone through Sir's lectures, you will know. Okay, we'll come to the answer, right? C is actually the correct answer for this one. This electrical synapse structure is basically a pore made of 12 proteins, right? 6 of which pass through each neuron. So 1, 2, 3, 4, 5, 6 over here, 1, 2, 3, 4, 5, 6 over here, right? So this is the first neuron, this is the second neuron. Overall 12 protein chains are there and 6 is passing through this one, 6 is passing through this one, right? So there is one connexon in each membrane which includes 6 protein chains or connexins. So overall they have 12 protein chains when taking into account the 2 membranes, right? Yeah. So which of the following channels can become inactivated? Passive sodium channels can become inactivated. Passive potassium channels can become inactivated. Voltage-gated sodium channels can become inactivated, or voltage-gated potassium channels can become inactivated. Which can become inactivated? Okay. So the answer for this one is voltage-gated sodium channels, right? So the passive channels are the ones that are always open, right? The leakage channels also. The voltage-gated potassium channels also are never inactivated actually, right? What is actually inactivated is the voltage-gated sodium channel. So this is another piece of information, right? Uh, yeah, a small depolarization can fail to generate an action potential. Why is this statement true? Because the leakage currents dominate over the voltage gated sodium channels, or the voltage gated sodium channels dominate over the leakage currents, or the voltage gated potassium channels are absent, or leakage currents are absent, or voltage gated currents are hyperpolarizing. Now again, we have not come to generation of action potential, but I'm sure you have gone through Sir's lecture, right? We have not revised it, but you have studied it. Okay. This is why I actually wanted to do the revision section first. Yeah. So in this case, The first is the correct answer, right? So why a small depolarization fails to generate action potential? Because leakage currents dominate over voltage gated sodium currents, right? So action potential requires voltage gated sodium channels, which increase membrane potential, right? Because equilibrium potential for sodium is towards the positive side to be larger than the leaky currents, which decrease the membrane potential, right? So once this threshold has been managed, then an action potential can be reached, right? Which of the following is true during the relative refractory period? The action potential is not possible at all. Action potential is possible with a larger than usual stimulus. Action potential is possible with a smaller than usual stimulus, or action potential is inverted, or that is, it is hyperpolarizing. Right? So there are two kinds of refractory periods, if you remember. So we are talking about the relative refractory period over here. What happens in this case? Okay. So what happens in this case is that it is possible, but larger than usual stimulus is actually required, right? Along with the graph, we will do it in the lecture, the discussion thing, right? So over here, in a relative refractory period, some of the voltage-gated sodium channels are inactive, right? So a larger stimulus is needed to open sufficient number of channels to generate action potential. Right. So why action potential is generally not being generated? Because sodium channels are inactivated. But if we give a very, good enough large stimulus, then it might be possible to open these voltage gated sodium channels so that we can generate this action potential. Right. Then question number 8. If myelination is removed from an axon, right, it is which of the following is more likely to happen? Okay. Conduction of action potential will become faster. Conduction of action potential will become slower. Conduction of action potential will become more energy efficient, or conduction of action potential will occur at the same speed. So what is myelination? Why is it needed? If you remember, it is a very, very simple question, right?
C.
See, will it become more energy efficient? So think of myelination as insulation, right? It is an insulating layer. If insulation is removed from a wire, will it become more energy efficient, or will it become faster, or will it conduct with the same speed, or will it become slower? There is more amount of
D.
dissipation of energy that will take place, right? If the layer of insulation is removed, which is why it will basically, it will become slower because the insulation or this layer is removed. So it can also be, you can also think of it as, yeah. So say you are heating something, right? Uh, there is this pizza that you have, and you have heated it in the microwave. It has been a while since you have had it, and now you want to reheat it, and you have heated it in a microwave, and you offer it to the person who is sitting in the kitchen itself, right, near the microwave, right? So over there it will be very hot, right? And if you go to another building to offer somebody that pizza that you have reheated, it will become cold because the energy or the heat has been dissipated because there you were just carrying the pizza around on a plate, right? Versus what if as soon as you heated the pizza, you placed it into a vacuum steel box, right? And then you took it to the other building, it will still remain hot, right? It will not be as hot as when you had just taken it out, but it will still be hot and much hotter than when you were just going with the pizza to the next building without any putting it in a box or putting it in an insulated box, right? So because the heat is getting dissipated in that case. So if the insulation is not there, the signal will be dissipated faster, right? Yeah. Then comes question number 9. The synaptic delay is smaller in chemical synapses than in electrical synapses. Now, again, we have not seen the difference. We have not revised the difference between the two. So, but what do you think? Is it true or false?
True, true. The delay is smaller.
In chemical synapses. Okay. What is going to be faster? Ion flow or electric flow? Like that is what is
Iron.
generating this. It is false, right? Uh, uh, Earlier, we were discussing this concentration gradient and electrical gradient. I was telling you, right, that concentration gradient is going to change slowly. Electrical gradient is going to change much faster, right? Electric flow is always going to be the fastest, right? So that is the same principle over here also. Chemical flow will be slower. Electric flow will always be faster, right? So that is why electrical synapses are faster due to direct conduction of ions from one neuron to the other, right? Over here, they are not even going to that, uh, uh, in the vesicles and lying in the synaptic region. That is not happening that much, right? This is a final question. A smaller stimulus will result in a smaller action potential in a typical neuron. Is this statement true or false? Okay. For this one, you have to just know one thing, that action potential does not have gradations. There is just action potential, right? It cannot be bigger or it cannot be smaller, right? If it crosses a threshold, it is an action potential. If it crosses it like by 10, it is still going to be this high. If it crosses it by 100, it is still going to be this high only, right? So this statement is false, right? So the size of action potential does not depend on size of the stimulus. Rather, it depends on the status of voltage gated channels, right? So, like again, another analogy over here that you can draw is um that. Let me think of a good analogy. Yeah, so if as simple as you applying a sick leave, right? So whether you are the number of days might vary. Similarly, the number of action potentials over here might vary, depending on whether you are a little sick or very sick, right? But if you are sick enough to apply a sick leave, right, that you cannot get out of bed, you cannot go to work, you cannot go to lab. If you are that sick, then you are going to apply a sick leave, right? Whether you have a fracture, whether you have been in an accident, whether you have multiple broken bones, whether you just have a very bad headache, or whether you just have a cold and you are not feeling like you have a body ache, you can't get up because of the cold, right? So all of these are different kinds of being sick, right? Some of them are more extreme than the other, but it is not going to affect the nature of leave, right? It is still going to be a sick leave only. It can affect the duration of leave, right? That over here, how many days? No, don't go into the duration terminology. How many days, right? Similarly, how effective a stimulus was could determine the number of action potentials it generates, right? But it cannot determine how, whether it will be a bigger action potential or a smaller action potential. That it can't say, right? So that is it for this part. Uh, Maybe I'll just share. Let me just look at the presentation, how much of it is left, and whether we'll be able to do a small section of it right now, the revision part that we were doing, right? Because I thought this will take time, but since we had already revised, it took much less time. Um, yeah, this is where we were. Okay, please. Patch clam still will not get over here. Hmm. A lot is actually left. So I'll just stop sharing the screen right now. Uh, it is very humid. I am also getting tired with just the yeah. Okay. So in that case, what we'll do is we'll end the session because in the subsequent ones, uh, I have scheduled 4 lectures. So the final one out of those 4 will be next Monday, 7 to 9 p.m. But of course, we are on a lag over here, and anyway, we do a final, extra session for any, doubts that you might still have left. So what we'll do is whenever we don't know, like we have not scheduled the fifth one right now, so I don't know whether it is going to be the following Monday after that. But if whatever part in this revision thing is getting left, that we'll probably continue in that additional session. So that we can do, right? So we'll not leave anything. We will revise the entire thing. Um for now, this will be it for this particular session, right? And as like some of you mentioned, if at all you are not receiving the update for or reminder for the session or the link for the session, the link is actually the same. So even if I keep an additional extra session, I will still keep the same link, okay? But that, of course, you will have to know like when it is. So probably I'll inform the NPTEL people to be particularly, uh, uh, be particular about informing everybody in that sense. For now, that will be it. If you have any questions, you are free to write to me. These days, I am a little busy. I have not been able to check the discussion forum, but I'm sure that Vaibhavi and Smith are replying you on the discussion forum, right? So in case you have any questions, we can address it in the class or you can write to me. Um, you can find my email ID. I don't know if it is now present. Mhm. Okay, so I'll probably mention it in the slide only, right? It is Arveen, Arveen K21 at iitk.ac.in. So, but I'll mention it somewhere so that you guys, if you want to ask anything, you can write over there. I will probably be more responsive over there than the discussion forum for now. Right. So that is it for the session from my side for today. We'll end it. Thank you so much for attending. I'll stop the recording also. I just forgot about that. Yeah. Yes.